is in detail with the array factor to know how null, maximum, 3dB point, maximum, secondary maximum are occurring as in broadside as well as endfire arrays. So we know the array factor formula, which is 1 by n into sine n by 2 into psi divided by sine 1 by 2 into psi. For nulls in the radiation pattern, this n psi by 2 is equal to plus or minus n pi. And for maximum amplitude, that is maximum grating, psi by 2 is equal to plus or minus m pi, where m is equal to 0, 1, 2, etc. The grating lobe conditions are considered at m is equal to 1, 2, 3. The 3 dB point will be achieved when n psi by 2 is equal to 1.39, and the secondary maximum of minor lobes occur when n psi by 2 is equal to 2s plus 1 by 2 into pi, where s is equal to 1 by 1, 2, 3, which are the spacings. The maximum of first minor lobe occurred at n psi by 2 is equal to 3 pi by 2. And as per the formula, the nulls occurred when n psi by 2 is equal to 0. And here we are having psi is equal to kd cos theta plus beta, which is equal to plus or minus 2n pi by n, where the number of elements n is equal to 1, 2, 3. So here the array factor is equal to 0, which is the maximum condition. When this theta n is equal to cos inverse of lambda by 2 pi d into minus beta plus or minus 2n by n into pi, where lambda is the wavelength, d is the distance, beta is the phase, n is the number of elements, and capital N is the number of array element. For the broadside array, this beta is equal to 0, and so theta n is equal to cos inverse of plus or minus n lambda by n into d. And for endfire array, beta should be minus kd, so theta n is equal to cos inverse of 1 minus n lambda divided by nd, where n is equal to 1, 2, 3. So based on this, we are having the null positions. And when we come for maximum position, this 1 by n is a negligible value, and so we may take it as sine n by 2, n psi by 2 divided by n psi by 2. So this maximum pattern may occur when the psi by 2 is equal to plus or minus m pi. So kd cos theta plus beta, which is equal to the psi, is equal to plus or minus 2 m pi, where m is equal to 0, 1, 2, 3. So the maximum angle theta m is equal to cos inverse of lambda by 2 pi d into minus beta plus 2m pi. For sin nx divided by n into sin x, the array factor formula, the maximum is occurred at x equal to 0 or psi by 2 equal to 0, that is m is equal to 0. So see here we are having zeros at x is equal to 0 and psi by 2 is equal to 0. Okay. So the grating lobe condition also we have to study over here. Grating lobe is the lobe with the maximum as of measure in other direction and unrequired direction. Maximum condition array factor was 0 condition, at which psi by 2 is equal to 0, or otherwise kd cos theta plus beta is equal to plus or minus 2 m pi. The broadside array is given as beta equal to 0, and the endfire array is given as beta equal to minus pi d. For beta equal to 0, theta m is equal to cos inverse of m lambda by d, where there is no grating lobe as long as d max is less than lambda. And for endfire array, theta m is equal to cos inverse of 1 minus n lambda by d, where there is no grating lobe as long as d max is less than lambda by 2. So this condition we have to check whenever we go for the maximum condition. And for 3 dB point, it should be sin x by x is equal to 0.707, where x is equal to 1.39 value. So the field pattern has been given as n psi by 2 is equal to n by 2 into the psi value kd cos theta plus beta for theta equal to theta h is equal to 1 plus 391, 1.391 as what given. There is a constant value. So from this we can write the theta as theta h, which is equal to cos inverse of lambda by 2 pi d into minus beta plus or minus 2.782 by n. So as we know, broadside array is having phase beta equal to 0, endfire array is having beta equal to minus kd. So the half power points should be theta h is probably equal to cos inverse of plus or minus 1.391 lambda by pi md. Theta h for endfire array is cos inverse of 1 minus 1.391 lambda by pi n d. And the secondary maximum occurs when 2s plus 1 by 2 into pi is occur. And the first minor lobe is at n psi by 2 is equal to 3 pi by 2 where s is equal to 1. So further we will get a value of the array factor value of minus 13 dB. When substituting in broadside array and endfire array, the minor lobe maxima has been given as theta s is probably equal to cos inverse of plus or minus lambda by 2 d into 2s plus 1 by n, where s is equal to 1 by 1, 2, 3. For endfire array where beta is equal to minus kd, theta s is cos inverse of 1 minus lambda by 2 nd into 2s plus 1. So for broadside array with beta equal to 0, d equal to lambda, we have theta m is equal to cos inverse of m lambda by d, which is equal to cos inverse of plus or minus m. Where the m exists and with the main lobe m is equal to 0, theta m equal to pi by 2, or if it is in the opposite plane, theta m is equal to 0 or pi for m is equal to 1. So this is the radiation pattern for broadside array, and when comparing with the endfire array, the values has been consolidated over here. Nulls occur at theta n equal to cos inverse of plus or minus n lambda by nd, where for endfire array where the angle shift is occurring, so 1 minus n lambda by nd will be given. So like that maximum occurs at theta m is equal to cos inverse of plus or minus m lambda by d. For endfire array, it is cos inverse of 1 minus m lambda by d. Half power points occur at theta h is equal to cos inverse of plus or minus 1.391 lambda by pi nd, where in endfire cos inverse of 1 minus 1.391 lambda by pi nd. Minor lobe maxima occurs at cos inverse of plus or minus lambda by 2d, 2s plus 1 by n, and for endfire it is cos inverse of 1 minus 2s plus 1 by into lambda divided by 2nd. So this is the difference, the phase, how the phase has been changed with the broadside and endfire array. So everything is based on array factor only. So the broadside arrays are having equal amplitude, equal phase, and the endfires are having equal amplitude and opposite phase. That's why this phase change is occurring. Thank you.